Hello, welcome back. This is Calculus by Dr. Oz. Today we're starting a new chapter, and in fact a new section called Basic Integration Rules. This is more of a revision of the integration techniques that we have learned in Calc 1 and in the first part of Calc 2. So we have only one learning objective, and this is to review procedures for fitting an integrand to one of the basic integration rules. This video is going to be a little shorter than the other lecture videos because this is more of practicing the integration techniques. So please spend more time on the recitation PowerPoint and their videos. Here are the basic integration rules. As you see, we have 20 of them. I think the first 17 were the subject of Calculus 1, and we added the last 3 to the list in Calculus 2. So we have 20 of them in total, and what we're going to do is to fit integrands to the 1 so we can use the basic integration rules. All right, here is an example. Number 1, we are going to compare 3 similar integrals. In fact, in each of them we have the bottom to be x squared plus 9. Only the tops differ, and you will see that we have a different technique for each integrals here. Let's start with part A. So we have the sum of the squares and we have a number at the top. So this is more of the application of the arctan rule. Okay, so it's arctan here, number 19. So it's the matter of choosing the right u and a. All right, let's do it for u equals x and a equals 3, so that we can pull out 4. Then we have 1 over x squared plus 3 squared. So we go ahead and use the formula to get that the integral is 4 over 3 arctan x over 3. So this was a simple use of the arctan rule because we have a number at the top. Okay, we have a number at the top. Okay, and the bottom is still the sum of the square. All right, let's stare at part B. We again have the same bottom, but this time the top is not 4, but 4x. So the arctan rule is not gonna apply, right? Because the numerator contains a factor of x. What we're gonna do is to use the log rule or u substitution, so that you call the bottom to be u, so x squared plus 9 is u, so that du equals 2x dx. Okay, let's go ahead and rewrite that integral. Okay, so du u equals x squared plus 9, du equals 2x dx. Here we go. You have 4 here, so why don't we split this as like 2 and 2. So 2x dx, x squared plus 9, so 2 times du over u essentially, right? So this is integrated as 2 times ln of u, and u equals x squared plus 9 plus c. So essentially this is 2 times ln u plus c, but u is x squared plus 9. So this is a good application of u substitution, or in other words, log rule. All right, let's stare at part C. We have 4x squared divided by x squared plus 9. Well, first off, the degree of the bottom is the same as the degree of the top, so that makes this rational function an improper rational function, whereas here we have proper and proper rational functions. So again, the known techniques cannot apply. You can't use the log rule, or you can't use the arctan rule. But what we're going to rely on too is the long division to rewrite this improper rational function as the sum of a polynomial and a proper rational function. And here's how you do the long division. So essentially you write 4x squared here, and then put the x squared plus 9 here. Okay, and now we put a 4 here, so 4 times x squared plus 9 is 4x squared plus 36. If you subtract, you have negative 36 here. So let's go ahead and rewrite this rational function. Here we go. We have 4 plus negative 36 divided by x squared plus 9. Okay, so we can split these two parts, right? Because one is a polynomial, the other part is a proper rational function. Okay, let's do that. So we have 4dx minus 36 times 1 over x squared plus 9dx. And this one, we can use the basic integration rule. 4 is integrated as 4x. And for this one, we're going to use the arctan rule because we have a number dividing sum of the squares. So this is like x squared plus 3 squared. So that arctan rule applies perfectly here. And here we go, 4x minus 36, 1/3 arctan x over 3 plus c is the answer. So as you see that we have three different examples here, and as you see that integrands look alike, but in fact they're totally different, and we have to rely on to different techniques that we learned in Calculus 1. Let's also recall some of the algebra and trig techniques that we used to use in Calc 1. For example, separating the numerator, expanding numerator, completion to the square, long division, adding and subtracting terms in the numerator, and using the known trig identities, and multiplying and dividing by the conjugate. So these were sort of like algebra and trig techniques. All right, let me just quickly remind you of those techniques on a simple example. So the first technique is expanding numerator. So if you have a quantity square term, and what we can do is to expand this out. This is a known algebra technique. You don't need to apply this technique all the time, but whenever it applies, it's powerful. Separating numerator. So we have a rational function, and at the top we have 1 plus x. So I can split this rational, or separate the rational expression as 1 over x squared plus 1 plus x over x squared plus 1. This is also powerful because as is, this rational function is not easy to integrate, but if you split that up, this is the first kind in the example, this is the second kind in the example that we have just went through. So you can use different techniques to integrate this function. Completion to a square. So we have 1 over radical 2x minus x squared. We also worked on this kind of problem in the beginning of Calc 2. So essentially you rewrite 2x minus x squared as 1 minus x minus 1 quantity squared. So this is called completion in the square. Okay. Dividing improper rational functions. When you have a rational function whose top and bottom have the same degree, then in the last example we had in this video, you can do the long division. Please do that, and then that way you have a polynomial and a proper rational function to integrate. You can also add and subtract terms in a numerator. Like in this example, you have 2x at the top, and then you have x squared plus 2x plus 1 at the bottom. We add and subtract 2, so that we can split this integral into two pieces, 2x plus 2 and 2 over x plus 1 quantity squared, because the bottom is in fact x plus 1 quantity squared. Okay, and this is also 2x plus 2, but when you pull it out, it's 2 times x plus 1 in fact. You can also use trig identities, sine squared plus cosine squared equals 1, or cotangent squared x equals cosecant x minus 1. This is another powerful technique to apply. And we can also do the multiplication and division by conjugate of the given term. So this happens generally when you have a rational function and the bottom is like the sum of either exponential or trig type quantities, sum or difference. So when we say conjugate of, let's say, the bottom term, what we mean by that is the minus version of that, and that you're dividing 1 over 1 plus sine x by that conjugate. Okay, and after you simplify the term, as you see that I'm using a trig identity here, because 1 minus sine squared x is cosine squared x, and you can rewrite this whole thing by separation of the numerator, 1 over sine squared x minus sine x over cosine squared x, and 1 over sine squared x is in fact secant squared x, and you have sine x over cosine squared x left. And for each of those guys, you can use one technique to implement to, if you're talking about integrating the function that you start with here. All right, this section, as I said, is the application of the known algebraic and trig techniques together with the techniques that we learned in Calc 1, like U substitution, log rule, and the basic integration rules. And let's go ahead and check out the recitation problems. All right, as I said, we have plenty of exercises that I went through by a step-by-step approach within my videos. Here is the warm-up exercise for you. You're going to use one of the 20 formulas to integrate each of these integrals. Some of them may look like familiar to you. So you have secant tan, there's a direct formula to apply that, or 1 over x squared minus 4. So go ahead and watch the video to see what I'm going to have to do for these 3 integrals. And in the second exercise, as I said, we have plenty of exercises for you to practice with me. So we have 6 integrals, and each of which uses an integration technique. Here we go. So this one and this one, long division. I'm just giving you some tips here. Multiplying by conjugate. Separation of the numerator, or multiplying by the conjugate, either one, whichever you would like to go with. Completion to the square, please practice that one. And this one is sort of like the expansion of the quadratic term here and simplifying the integrand. So as you see, like, this is a combo of carefully picked, nice the exercises, integrals that you can practice what we had in this list here. I'm trying to use almost all of them here. All right, the next exercise in the list is solving differential equations. We have seen that in Calc 1. Essentially, solving a differential equation means finding the integral of this term. Essentially, y here is the integral of 4 minus 2x quantity squared dx. So solving a differential equation in this context is just to find the integrand of integral of this function, and in part B, integral of this function. But we're going to obviously practice those integration techniques. So in the first one, we're going to use the expansion. In the second one, we're going to use the expansion and separation of the numerator type techniques. So please go ahead and start solving those problems by yourselves. And I also added 4 more exercises for you to practice with the definite integral versions of integrals. Essentially, you're going to do the same thing. You're going to apply the same or similar techniques, but this time you have definite integrals. So you essentially get a number at the end, but the first part is to integrate these integrands, okay? And again, you can use U substitution, separation of numerators. So you're going to use all these techniques in the list, and please watch the videos to see what I'm going to have to do to take care of these 4 integrals here. And finally, this is not the end of the story. Finally, we have a good application type problem because we have just seen the calculation of arc length in the previous chapter. So I put y equals ln cosine x, and I was asking to evaluate the arc length for the piece, for the segment corresponding to the interval 0 and pi over 3. Again, this is an application type problem. Please go ahead and practice these techniques to evaluate the arc length integral. So the answer for that, it should be a number. All right, now it's U o'clock. It's your turn. Please go ahead and start solving the recitation problems. And once you're done with those, you can perfectly start your homework problems and even quizzes involving this section. All right, thanks for watching. I'll see you in another video. Bye.